Welcome to session number 15 in analog circuit design using ADS. This is Anurag Nigam, and in session 14 I had shown you two op-amps, right? One which is a two-stage op-amp, which is over here, and then there is a three-stage op-amp. Now what I'm going to do is I am going to use this as a component to design circuits, right? So op-amp based circuits. So I want to do first text based circuits, like for example for the beginners, right? So they are interested in something like, inverting amplifiers, non-inverting amplifiers, integrators, differentiators, oscillators, right? Then let's say IC555 and things like that, right? So you can design all this using op-amps. So I'm going to demonstrate how to do that. So first you make a folder and say op-amp circuits, right? So I'm making a folder and I'm copying the op-amp over here. So there is a two-stage op-amp here, right? So I'm going to say copy cell, and I'm going to copy this as C. So whenever I put a C following it, it means that it's a component. So that's my naming convention, and I'm going to put it inside here and say OK. So once I'm done with it, this is over here. What I do is I'll throw out all the sources and make a component for this. So this is operating from 2.4 volts. So I have one more convention which I follow. Wherever I put a pin, I also put there what I'm expecting as a voltage, right? So that's my naming convention here, right? And then secondly, I need a IREF. Similarly for IREF, I'm expecting a 20 microamperes of current, so I will say 20 microamperes, right? So that's my expectation of the current here. So that's what I will do here, and I'll get rid of the sources. Okay, next is I have got this as a non-inverting amplifier, right? So non-inverting input, right? So first of all I'll do the ground. So for ground there's nothing special, just say ground, and this ground is over here, correct? So this ground is over here. So the ground is done. Then I'm going to have a non-inverting input, so that I would have it over here, right? So NINV, non-inverting, right? So I'll keep it here, and then I have an inverting input here, so I will do INV, right? And let me just rotate this. Okay, let's see what this is. I have cleared this earlier also, right? So when this one is going to go low, this node is going to be pulled up, which means that this is going to be pulled down. So when this goes high, this node goes low, right? So when this node goes low, then this goes high. So that's a non-inverting input. And then I will also remove the naming here, and I'll put here a pin. So that will be VO, right? And yeah, so I'm just going to do a rotation. So that's a VO, and I'll get rid of all of this stuff. So that's my component. So just to be sure that everyone can see all the names, all the pins are there, right? And I have named them such that I know what they are, right? And what voltages and currents to connect, right? So this is a two-stage op-amp, right? If you want, you can put a remark also, two-stage op-amp. ADS also allows you to do a what you call a sheet, right? So if you go here, I just want to, sometimes documentation also becomes important. Like, so for example, if you go in driving format, and this is the smallest sheet, so it doesn't fit here, right? So that's a bigger sheet, right? So when you work in a company, right, so you are supposed to do something like this. So say view all, Okay, so it looks like that. So what you can do here is you can put your contact number, name, title, what it does, and stuff like that, right? So here another thing is you can do a version control here, right? So this for documentation, this is very good, right? So all I'm going to do is I'm going to put my name here. So you just say insert text, and you just put your designer's name, for example, and you can put a date and revision number and all that stuff. So I will just say a two-stage OpAmp, right? So that's there. So this is one good way of documenting it. Now once you're done with this, all you do is right click this and make a symbol for it. So here I have made a symbol which is a generic symbol, so I'm going to replace it with my own symbol, right? So I don't want to be very big, I don't want it to be very small, something in between. So let's say something of this size is okay, and then these two pins will come at the bottom, right? So usually these two pins will come at the bottom. One of them is going to be the current reference, other of them is going to be ground. Then you have got inverting at the top, so I can always do a mirroring also like this, right? So inverting at the top and non-inverting at the bottom, right? And then I can put a output pin over here, and then I can put a supply pin at the top. So that's the supply pin. Now sometimes there is a grid issue, but I will tell you this. For example, here there is a grid issue, right? So if I try to extend this, yeah, it goes inside, right? So you can turn off the grid, but don't move the pins with the grid off, because then you will have connection problems in your higher level of schematics. So once your pins don't move the pins with the grid off. That's all what I'm trying to tell you. You can move the text and everything, that's fine, but don't try to move the pins. Okay, so I'm going to turn that back on, and I'm going to insert a small text to remind me it's a two-stage. So I'll put here a text which says two-stage OpAmp. So that's a two-stage OpAmp, right? So if you are saying text is too big, you can go here and change the size to be half of it. Let's say 0.8, and that's it. So that's a two-stage OpAmp. Okay, so now we have a component for a two-stage OpAmp, right? Next is if I want to do a three-stage OpAmp, I'll have to do the work again, which I don't want to do, right? So I would just say copy cell and make it a three-stage OpAmp over here. Three-stage OpAmp, and it's a component, and it goes under this folder, right? So that's a three-stage OpAmp, right? Now I'll just go ahead and modify this. Okay, so what I have to do is I have to introduce a stage over here, right? So I'll go to my three-stage OpAmp here, and here the only thing which I have to copy is this thing. I don't even want to copy the name. I'll say Control C. Sorry, I'll say Control C, and then I'll come back to my three-stage here and say Control V. Didn't do it. Okay, I'll do it again. Okay, so go over here, copy these two transistors, Control C, and there they are. Okay, so I'll just connect them. So this goes there. Just bear with me for a minute, I'll be ready. this is coming from here, this is sitting in its well, so body is connected to the source, this is the output, and this is coming from the supply, right? Okay, so now I'll just center it out so that everything is inside. Okay, so now this is a 3-stage OpAmp. Just I'm gonna make sure everything looks okay. How come this is 20? It should have kept it 40 itself, right? Let me check it. That's the one, right? 40, right? So this is 40, this is 40. I don't know where that came from, 20. So this is also 40. Okay, sometimes it plays. Oh, that's the reason. Okay, sorry. The reason is it has copied these transistors. That's not what I wanted to do, right? But anyways, I'll just repeat this transistor over here, and now the body connection is wrong because this is a common drain, this is a PMOS, right? So it's connected over here, and these okay, this one, let me move the text so that things are visible clearly, right? So it's clear. Okay, so I must make sure this is a PMOS, this is a PMOS, same size, this is a mirror, this is a follower, and remaining OpAmp is the same. I'm going to just change here text to be 3-stage OpAmp, right? So remaining things are the same, and even the circuit will remain the same because there are no additional pins here, so I can use the same symbol, right? So this is a 3-stage circuit, right? And in this symbol I'm just going to change this to 3-stage so that I don't get confused, right? So this is a 3-stage OpAmp. Done. So I have, let me verify this. This is a 2-stage and that's a 3-stage. Fine. So I have 2 OpAmp components over here, 2-stage and 3-stage. Now what I'm going to do is I'm going to try some circuits, right? And you can try any circuit in the textbook you like. I think it should work, right? So let me try here a IC555. So sorry, IC555. Now how does this work? Okay, let's see. So we have got VDD, and then we have got the famous 3 resistors which are each 5K, right? And then we have got what you call comparator. So these OpAmps are comparators. So these OpAmps are nothing but they are high gain stage, they are used open loop, and they are just a comparator. So let's say that this is a inverting input and this is a non-inverting input, this is an inverting input and this is a non-inverting input, right? So just one second. Okay, so what you do is you are having inverting input connected here, and I call this one as a threshold. So this pin is called threshold, right? And then in this case there will be opposite connection. Non-inverting is connected here and inverting is over here, and I call this as trigger, right? And then when you come out of it, you have a SR flip-flop or SR latch. So I'm going to do a, so this is R, this is S, this is Q, and this is QBar, right? And then this is connected to the supply. Yeah, so there is a supply here for this VDD and there is a ground here, right? So this is my SR latch, right? And then the output of the SR latch I am going to put here, for a Q I'm going to put here a PMOS. So for a Q I'm going to put here a PMOS, right? And this I will call as discharge 1. Okay, and this will go to ground. So this is going to discharge thing to ground. And in this case I am going to put an NMOS. So this is going to be out, and I'm going to put here an NMOS transistor. That is going to be, so if I call this discharge 2, this would be discharge 1. I can use either of them to get this into. Okay, so this is the basic circuit. And how does it work? It works this way. You have to specify in this case, because in a real circuit of course you can just switch on the circuit and it'll start working, but in case of ADS you have to place this in the region where it's going to operate. So that means that the initial starting point, right? So if I was to do a vibrator, so what you call Astable multi-vibrator, right? Then what do? What I do is I will have a capacitor connected to the threshold, right? So I will have a capacitor connected to the threshold to ground. Okay, and then I will have a discharge node, right? A discharge node to discharge this capacitor, and then a charge node to charge the capacitor, right? So I can charge the capacitor from here, and then I can discharge the capacitor. Sorry, why did it change? Okay, so I can discharge the capacitor from here. So this will go to one of the discharges to discharge the capacitor, right? So this is discharge. Okay, so what happens is this capacitor, okay, gets charged, right? And when this voltage, okay, okay, so there is a set. Just one second. Okay, so what's gonna happen is, even this is connected over here, right? So let me just connect this one over here. Okay, so I'm sampling the voltage on the top of the capacitor, and I know because this 555 there are 3 of them, then the voltage at the inverting input here is 2 by 3 VDD, and voltage here at non-inverting is 1 by 3 VDD. Okay, so now if initially what happens is this capacitor, okay, let's say is charging and it's in this range of 2 by 3 and 1 by 3. So let's say that there is 2 by 3 VDD, and then there is 1 by 3 VDD, right? And and the voltage is somewhere in between on the cap, right? So the voltage is somewhere in between on the cap. So now let's say that then let's assume one of the states. Okay, so one of the states here is going to be, so if that, right, so if it is in between, then what's going to happen is the output of this OpAmp is going to be 0, and the output of this OpAmp is also going to be 0. So it is going to maintain the previous state, and the previous state can be charging or discharging. So let's assume that the previous state is basically reset. Okay, so now what is going to happen is yeah, so now it's in the discharging phase, right? So this point is connected over here, discharge 1, right? So this transistor is on, right? So when this transistor is on, this capacitor is discharging and voltage on the capacitor is declining. So the voltage, so let's say we start from here, the voltage is declining. As soon as it crosses 1/3, what's going to happen is inverting input, okay, is lower than 1/3. Then what happens is non-inverting is higher, then this becomes 1. So this will now become, sorry, okay, so now let me just reduce the size of eraser. Now this has become 1. As soon as this has become 1, okay, this is going to set. So when it sets, this becomes 1, this becomes 0, so this transistor switches off. So when this transistor switches off, okay, then the discharge stops and the capacitor starts charging. So capacitors keep charging, and when it crosses 2/3, okay, this one becomes 1, right? So this one becomes 1, and then this one is 0. So when it is in this stage, when it is in between here, the output of both op-amps is 0, but then it has maintained its state, right? So once it maintained its state, it was discharging and then it was charging, so it has maintained its state of charging. When it crosses 2/3, this becomes 1, and this was 0 to start with, because in this region everything is, both are 0, right? Both outputs are 0 in this so op-amp 1 output is 0, op-amp 2 output is 0 here. Now this is 1 and this is 2. Okay, so let's put there 1 and 2, both are 0. Now at this point what happens is output of 2 becomes 1 and output of 1 is 0, right? So output of 1 is 0, and this one, so it was set, and when it was set, it stopped discharging, right? So just 1 second. Okay, so now it has again changed, cross 2/3. So in this region, I is going to become 1. Sorry, I is going to become 1, or rather 1 is 1, and this is going to be 0. So now it's going to reset. So once it resets, this will become 0 and this will become 1, right? And that means that this transistor turns on, the discharge one, this transistor is going to turn on, and then the capacitor will start discharging again, right? So when it comes back to this region, it will again become 0, 0. Okay, so it will again become 0, 0. It will maintain its state till it hits 1/3 again. So it will do this, right? It will keep doing this across the across the capacitor. It is keep doing this, and what happens with the output is going to be between 1, it will always toggle 1, 0, 1, 0. So basically you have generated a square wave at the output and a triangular wave on the capacitor. So this is a 555 configured as what you call a stable multivibrator. So this is what I'm going to implement for application of OpAmp, right? So let's go ahead and do this. Just 1 second. Okay, so I am going to make here a new schematic. Okay, and first of all I'm going to make a what you call SR latch. Now I want a SR latch where 0, 0 input causes the state to be retained. That means that it has to be a NOR gate, right? Not an AND gate based. Okay, so now I am going to put here SR latch. Okay, and then also I will have to put here a new if you are following my series on digital design, these sub blocks are already there, digital blocks, right? So I'm also going to make a NOR gate, NOR 2 input NOR gate. Okay, so first of all, the NOR gate part. So for NOR gate, what do I need? I need an NMOS and a PMOS, right? So let's get it from a common source. I don't want to, or common gate for example. Okay, I'm gonna pick up this one, and this is a NMOS, so this one, Control C, and I don't need this anymore. Control V. Okay, so now here I want to make them very small. So this is 130, and this is, let's say, 6. 6 is okay, and this one is 130. So this is the minimum feature length. Let me see if I'm recording. Yes, I am. And this one is 2. Okay, so in a NOR gate, what do you think we are going to have? You are going to have 2 PMOSes like this and 2 NMOSes like that. Okay, and let's make this 4, and let's make this 4. That's fine. And what I'm going to do is I'm just going to connect them to their individual sources, the body connection, and in this case it will be going to the source here. Okay, and then these are connected this way, and this is one of the inputs, and this is another input, and this is going to the output, and this is going to the ground. So we are done with the NOR gate. So all I'm going to do is I'm going to put here some pins. Okay, pins are going to be VDD, and then ground, right, and then you are going to have A, which is going to be any one of them, and then you're going to have B, which is going to be the other one. Okay, and then you are going to have a output pin, which is going to be Q. Okay, so that's a Q. Okay, so all I'm going to do is connect them, VDD, ground, A, and B, and Q. Okay, so this is my NOR gate. Just let me make sure everything is connected properly. Yeah, fine. Now I'm going to make a symbol for this one. So here's my NOR gate. I'll say new symbol, create symbol, and say OK. And I don't like this rectangular symbol, so I'm going to make my own. Okay, so let me choose an arc, insert an arc. Let's say I am going to go this way, so let's choose this to be medium. Okay, is it going to be too big? No, that's fine. Control C, Control V, and flip it out and connect it. And then I am going to have one connection over here, so one more arc, and that's that. And here again, I don't want it to be thin, I want it to be medium size. Fine. And I have, this is a NOR gate, right? So these are my AB inputs, so they are going to go here. So kind of not adjusting, that's okay. Okay, so these are my A and B inputs, and then I'm going to have a NOR gate, right? So Q output, which I'll keep over here, and then I have a ground, which is over here, and then I have a VDD, which is over here, right? And I'll get rid of this stuff, and then I will switch off the grid for a time being and adjust this. So again, caution, don't move the pins with the grid off. Okay, so I'm also going to insert this guy a small bubble over here. That's a small bubble here for the NAND gate, sorry, NOR gate, and I'm done. I'll turn back on the grid. So that's an NOR gate using so that's an NOR gate. So now I have to make a latch, SR latch. So let's connect this. So let me get two NOR gates, right? And then these two NOR gates are connected together on VDD and ground, correct? And then they are cross coupled. So this comes here, and this comes here. So these are cross coupled, and then you have got two terminals, right? So let's figure out what they're going to be. Okay, just 1 second. Okay. Okay, so I am going to have this one as a reset, and this one is a set, and this is Q. So this one is a reset, and then I have a set over here, and then this is Q. So let me get the Q here. That's a Q, and that's a QB or QBar. So that's a QBar. Okay, so these are inputs and outputs, and then I'm going to have two more pins because this is a real circuit. So I'll have a VDD, so I can connect VDD here, and then I have a ground, which would be over here, and I'll just connect them. So this is my VDD and this is my ground. So let me check. VDDs are connected, grounds are connected, R is with Q, S is with Q bar, this is a cross coupled, and save. So I am going to make a symbol for this one, right? So this is a SR latch, so let me make a new symbol. Say okay. Now SR latch is almost always the same, so it's just that I am going to just shrink the size. That's all I am going to do. Okay, this is good enough, and this is good enough. So that's a VDD, and that's a ground, and I will put here a little text here which reminds me that this is a SR latch. So I'll say insert text. I'll put here SR, and I'll put here the SR latch. So that's my SR latch. Okay, so I'm ready with all the subcomponents, right, of this IC555. Then what I have to do is I have to just generate a 555. So I'm going to go here and say, sorry, I'm going to go ahead and say new schematic, and I'll call this as IC555, right, and say create schematic. And then I'm going to take 3 resistors, right? So let me just have a resistor here which is a 5 kilo ohm, right? So this is a 5 kilo ohm resistor. You can have any resistor value, doesn't matter, but this is historic, so I am going to still keep it 5 kilo ohm. And then I have another 5 kilo ohm. Okay, okay, and yeah, understood. Okay, So I am going to just create one, and this side it's going to be VDD, right? So this side is going to be VDD, and this side is going to be ground. Okay, so let me just do a view all so that you can see. So this is VDD and this is ground, and usually they have a control pin, and this is for setting the initial stage, CNTL, because so this is for setting the initial state. This is a control pin. I'll connect it over here, right? Then I'm going to have two OpAmps, so I'm going to use a 3-stage OpAmp here, right? So the inverting is at the top, right? Okay, inverting. Okay, it's two OpAmps, and then I have to bias them. See, what happens is there is a bias circuit which is on-chip bias. So I'm going to talk about on-chip bias later on. So for now, I can put here a 20 microamperes, right? So I'll go to sources, frequency domain, and I'll put here two of them, 20 micron each, or 20 microamperes each, sorry. So this is going to be 20 microamperes, and this is going to be 20 microamperes. Okay, so the biasing part is done. Let's keep it on this side, doesn't matter. Okay, so I am going to move this text to the top, move this text to the top here. Okay, so now this is connected to ground, this is connected to ground, this is connected to ref here, and this is connected to the ref here. Right, and then these are connected to ground. Right, and then these are connected to supply to power on our OpAmps. So that's connected to supply. The OpAmps are connected. Now inverting is connected to here. So if you see, inverting is connected to 2/3. So this inverting is connected to 2/3, and here non-inverting is connected to 2/3. Right, and then you are going to have a SR latch. So I'm going to bring in a SR latch over here, and let's zoom in. Okay, so this one is serving the R terminal, and this one is serving the S terminal. This is connected to VDD, and this is connected to ground. Fine, and then there is going to be a PMOS and an NMOS. Right, so NMOS is connected to set or QBar, right? Sorry, so NMOS, I'll borrow NMOS from within the SR latch itself. Within this, so I want to borrow one NMOS and one PMOS. Control C, and then here Control V. Okay, so the NMOS is connected over here. So this is going to be the discharge pin. So this is driven by QB. Right, and then the PMOS. Okay, I am going to have PMOS option also open, and this will be connected to ground. Both are discharges. This is connected to the set. Okay, so let's just connect two more pins here, 2 or 3 more pins here. So this one is called the trigger, and that one is called the threshold, right? So I have a pin called trigger, which I call TRIG, trigger. Okay, so this is called trigger, and then I'm going to have another pin which is called threshold, TH. I'll just call it a THOLD. Okay, so this is called threshold. Correct. And then I have discharge 1, discharge 2, and out. So I'm taking out from the same terminal, right? So I can take any of the terminals out, or if you want to have out 1 and out 2, you can do that also. So I will do O1, O2. Okay, so O or Q bar, I can still do Q bar, right? So I will do a Q, which is going to be connected to this one, and then I'm going to have a Q bar, which is going to be connected to the other one, right? So I'm observing Q bar at the output. Q bar, and then this is discharge 1 and that is discharge 2. So this 1, this 2. So I'm going to have this 1, right, and then I'm going to have this 2. So this 1 and this 2. Okay, let me make sure I'm recording it. Yeah, I am recording it. Okay, so now I'm ready with IC555. I'm going to make a symbol for this one. Let me just do one thing. Let's make this as a bigger size, and let's make this as 6. Okay, so our RDS, or rather the channel resistance, is going to be smaller. I want the channel resistance to be small here when it is fully on. Okay, so this is IC555. Anything left to do? Nothing, right? So let me make a symbol for it. Now QB usually not available in the there are 8 pins only for this IC, right? But I'm going to have 9 pins, so don't mind that. Okay, so let's go here and say new symbol, say okay. So I am going to just change this slightly. So I am going to have a VDD. Try to have as close as possible to what is available, right? So I'm going to have a VDD over here. Okay, and then I am going to have a ground over on the other side. So that's the ground, right? VDD ground, and then I'm going to have discharge threshold and control. Okay, so discharge threshold and control and discharge 2. Okay, so I have discharge threshold and control. Let's keep this out. Discharge threshold and control. Fine, and then I'm going to have Q, trigger and out. So trigger and out is going to be Q. So this is trigger and out, and this one is discharge 2. Okay, make sure that discharge 2 is grounded, otherwise it will draw current, right? Okay, now what am I going to do with QB? let's see that where I adjust this QB. So I am going to adjust this QB over here. This is not what you get usually, right? So usually you do not get that, so I'm still gonna keep it QB. And okay, and I'm gonna turn off grid, right? Okay, so this pin is usually not there in a IC, right? But it's okay, I'll just put it there. Okay, so that looks okay for me. So just to remind that this is going to be a bar, I'm going to turn back on my grid. Okay, so this is my IC555. One more thing is left, which is not very important, but I still put it there. Okay, so I want to do, oh, it's opposite side. That's okay, I'll mirror it out. And I'll put this over here to say that this is the IC, and I'll put here a label. So I'll insert a text here saying that this is IC555. Okay, done. So we have designed a IC555. Now let me make sure grid is on. Okay, now I'm going to configure this IC as a Astable multi-vibrator. So I'm going to go here and create a new schematic and say Astable. Okay, LTI, Astable multi-vibrator. And I'm gonna have a IC555 in here, so that's my IC555, right? F5, the text I'll keep here. Then I'll connect VDD and ground, and discharge 2 is also ground, right? So that's what I'm gonna do. Okay, and control I'm going to put to ground with a capacitor. Right, so I'm going to choose here a small capacitor, lump components. I can leave it floating, or it's good to do. So in real circuit, you'll not terminate like that. It'll just leave it floating. That's okay. I'll just put here 20 femtofarad, 20 femtofarad, correct. And then discharge is connected to ground. So discharge is connected to ground. And what else is connected to ground? Okay, I'm also going to look at the output on Q and QB. So I'm going to put the same 20 femtofarad as load. So I don't want to load the output node. So one is going to be Q and the other is going to be QBar. Correct? Okay, so you're not going to see this terminal in the IC, right? So how it is configured. Now what about the capacitor? I am going to, so basically a frequency is going to decide this capacitor. 1 over RC time constant is going to be tau, right? So you can calculate that. So I am going to put in here a big capacitor, 69 nanofarad, correct? And then, so this is my threshold, and both, so this is my threshold as well as my trigger, right? So I can bring the trigger this way. So these two are the same terminals, and then the top of the this I'm going to have a charge discharge resistance. So this RC time constant is going to decide your frequency. So let's say this is 100 kilo ohm. So this is, let's say, 100 kilo ohm. So this is 100 kilo ohm. Okay, and then I'm going to have just 1 kilo ohm on top of it. So I have just 1 kilo ohm on top of it, right? And this terminal is going to be connected to discharge. So this terminal is going to be connected to discharge. Then all I need is a VDD and a ground to this. So this terminal is grounded. So this terminal is grounded, correct? And I'm just going to apply a supply, right? So a supply is going to be a 2.4 volts, let's say. So I'll go to sources, frequency domain. I'll put 2.4 volt supply over here. Okay, 2.4 volts supply. And now is the time to label the pins, right? So it needs a ground done. So, oh, and this is connected over here. So yeah, done. So we are done with this, and then I need an include file. That's the include file here. I need to label. So this is Q and this is OP. So I'll put here a, so I'll name the nodes. So let's say this is going to be CH. It shows charging and discharging. And this is going to be Q, which is your output. And then QBar, which is your second output, correct? And we are all set to simulate this. So I'm going to simulate for 100 microsecond with a step off. So I'll go to transient simulation, transient, and I'm going to do this for 100 microsecond, steps of 0.1 microsecond, 0.1 microsecond, correct? So other than that, I think I'm all set, right? Okay, so I'm gonna just simulate this and see what happens. If all is well, it'll work. Otherwise, I'll debug it. Okay, so let's look at Q. Okay, so Q is working fine, other than something is happening over here at the time of charging. That's okay. So this is between 0 and 2.4. So what I can do is I can plot it from 10 onwards, right? So I will go here, plot it from 10, what is it, 10 microsecond, right? So 10 micro, what, hang on, x-axis, why is x-axis in microsecond, right? So if I put here 10 e minus 6, and this is 100 e minus 6, 100 e minus 6, and the step is going to be 1 e minus 6, isn't it? No. Okay, so that's done. Let's make it bold. Okay, so this is your output, and Q bar is going to be the opposite of it, and Q bar is going to be opposite of it. Let's draw a dotted line. Correct. So now you see that this multi-vibrator is working fine, like a IC555, and on top of it, if I want to show here what is happening with the capacitor, and this capacitor is doing that, and if you look at 2/3 of 2 point, so let's see if it is going from 2/3. So over here 1.6 volts, 8, so is 1.6 2/3 of 2.4? Yes. And then marker new, this is going to be 8. Is 8.8 1/3 of 2.4? Yes. So you have this. This is how your Astable multivibrator using 555 works. There's a capacitor which is being charged and discharged, which you see over here as this magenta line, going between 2/3 of VDD and 1/3 of VDD. And then there is a comparator. That comparator is basically two OpAmps acting as comparators, which are driving a SR latch. So this is the output of a SR latch, right? And this is how a stable multivibrator with a IC555 works. So here I'm going to conclude as the first application of an OpAmp. An OpAmp in this case is being used. So let me go down in hierarchy. These OpAmps are used as integrators, as an open. There's no feedback, like, so they are operated open loop with a very high gain, and the gain is around 60 dB, right? Okay, so the gain is around 60 dB on each OpAmp. So they are acting as comparators. Now, comparators are slightly different than just a open loop OpAmp. They have to have something called hysteresis, right? So that I'll talk when I design comparators from OpAmps, right? So I'm going to conclude the session number 15 over here, and thanks a lot.